and welcome back to this series on multivariable calculus. Today we're going to be talking about Taylor series, but for functions of multiple variables. So let's assume that f maps R to R, where f is infinitely many times differentiable. Then the Taylor series of f centered around the point x is equal to a is given by this infinite series, where this particular expression, which is just a number for each k, is sometimes called a Taylor coefficient, and then this is the associated polynomial term for that particular index k. So that is what we call the Taylor series, which gives you the approximations of any order to a particular function. So if we take a look at our particular function f, and let's assume that f maps R2 to R, from our discussion on tangent planes, we were able to see that f of xy is approximately equal to f of ab plus f of x ab times x minus a plus fy ab times x minus b. So we already have verified that this is actually our first order approximation, and one can actually show that this is equal to the first order term of the associated Taylor series. But let's assume that we want to find more terms in order to make this approximation more accurate. So the guiding question here is, can we get a higher order approximation to f around the point AB? And the answer is, of course, yes. So the higher order Taylor series is going to be of the following form for one particular variable. So recall that f of x is equal to, again, f of a plus fx of a times x minus a, and then plus f double prime of x at a all over 2 factorial times x minus a squared. So this term right here is our second order term. And then, of course, over here we have our higher order terms, hx of order 2. Here, this is what I'm referring to as hx. So how would this extend to multivariable functions? So in case you don't remember how to sort of evaluate this, pretty much what you do is you take the derivatives, evaluate at a, and then solve for the associated term of interest. So one can show that for two variables, f of xy, what we're going to have is the following. So we're going to have f of a, b, plus fx ab times x minus a, plus fy ab, and then y minus b. So here is your first order term. And then we're going to have our second order term, which is still going to have your 1 over 2 factorial, but for second order derivatives, you're actually going to have 3 terms, xx, yy, and the mixed partial xy. So what will that look like? So we're going to have fxx at ab times x minus a squared. Then you're going to have the mixed partial fxy ab x minus a times y minus b, and then fyy ab, and then we're going to have y minus b, the quantity squared. And keep in mind, these are your second order terms. So these are your second order terms. And then you're going to have some more things, plus o, and that's going to be hx to the power of 3, and then hy to the power of 3, right? Where hx will be equal to x minus a, and hiy will be equal to y minus b. And you can, I leave as an exercise, write out what the third order terms would be, the fourth order, and so on, via a combinatorial summation expression, but that in some sense is how you find higher order Taylor series. Now let's go through a numerical example on how to find one. So in the last video, we explored how to construct tangent planes to curves, which pretty much gave linear approximations to those curves. Let's assume that we actually want a little bit more of a higher order approximation to that curve. For example, let's say a parabola or a parabolic approximation, i.e. a second order Taylor series approximation. So how would we do that? So let's assume that our function of interest is sine of x squared plus xy. And let's assume that the point of interest that we desire to approximate around is the point 1, 1. So how are we going to do it? So the first thing that we need to do is get our first order derivative. So fx at, for example, xy, that's going to be equal to what? So the derivative with respect to x is going to be equal to, so keep in mind y is a constant here, so that's going to give us 2x plus y multiplied by the cosine of x squared plus xy. Now what I want to do is also find the first order with respect to y. So that's going to be fxy is going to be equal to, so x squared will be a constant, so that's going to be equal to x times the cosine of x squared plus xy. So those are the only things that you need for a linear approximation. Now we need to construct the three second order partials, xx, xy, and yy. So to find fxx, we're just going to take the partial derivative with respect to x of fx, and that's going to give us fx. So we have two functions multiplied together, so we need to use a product rule here. So let's do the first times the derivative of the second. That's going to give us a negative sign term. So that's going to give us minus 2x plus y, the quantity squared, times the sine of x squared plus xy. And then we're going to do the second, which is cosine of x squared plus xy, times the derivative of the first with respect to x, and that's just going to give us 2. We're going to do the same for fyy. So fyy, xy is just the second derivative of f with respect to y, so y on the y term. So that's actually very, very simple because x is just a constant. So the derivative with respect to y again will be equal to minus x squared times the sine of x squared plus y. So that's actually very nice. Now fxy, which is the same as fyx by Clairaut's theorem, since sine x squared plus xy is a smooth, everywhere continuous function, including its partial derivatives. So we can do, for example, fxy to be equal to the partial derivative with respect to y of fx, xy, or you could do the partial derivative with respect to x of fy, xy. You'll get the same exact answer. Regardless of the direction you take, you're going to get something of the form. Let's take the derivative, for example, of x and then with respect to y. So that's going to give us minus, what is that, 2x plus y times x times sine of x squared plus xy. And then we're going to have plus cosine of x squared plus xy. And then that's going to give us 1. Right? So those are our second order partial terms, right? And if you're curious where that 1's coming from, that's the derivative of y with respect to y, because 2x is just a constant. Right? So that is going to be our mixed partials. So now we're just going to evaluate all of these at our point 1, 1, and that's going to give us our approximation. Right? So f11, our 0th order approximation, which is going to be equal to the sine of 2. Keep in mind we're going to be in radians here. This is going to be approximately equal to 0.91. Now let's do our first order. So we're going to have fx11. That's going to be equal to 3 times the cosine of 2. And then we're also going to have fy of 11, which will be equal to the cosine of 2. And those are going to be equal to approximately negative 1.25 and negative 0.42 respectively. Now let's figure out what our values are for our second order derivative terms. So we're going to have fxx 1, 1. We're going to have fxy 1, 1. And fyy of 1, 1. And those are going to be equal to, at least in exact form, minus 9 times the sine of 2 plus 2 times the sine of 2. Then we're going to have minus 3 times the sine of 2 and plus the cosine of 2. And of course verify these to make sure you know where these are coming from. And then negative 1 times the sine of 2. And they're going to be approximately equal to negative 9.02 to the 2 decimal places, negative 3.14, and negative 0.91 respectively. Once you have each of those terms, now we can build our quadratic approximation to our sine x squared plus xy function. So that means fxy will be approximately equal to our 0th order approximation, and then plus our first. So negative 1.25 times x minus 1 minus 0.42 times y minus 1. So once you simplify that out, that's going to give you your tangent plane. And then we're going to have 1 over 2 factorial, which is just 1/2. And then we're going to have negative 9.02 times x minus 1, the quantity squared. And then minus 3.14 times x minus 1, y minus 1. And then minus 0.91 times y minus 1, the quantity squared. And then we can add the cubic terms if we really have a desire to have a better approximation. So once you distribute those, FOIL those out, and simplify everything, and hoping I didn't make any mistakes in this calculation, your second order approximation will be, in descending order, negative 4.51 x squared and minus 0.455 using these 2 decimal place accuracy values, and then y squared, then minus 1.57 xy, so those are all of our higher order terms, and then our linear terms, positive 9.34x, positive 2.06y, and then our constant term 3.955, right? And that is our quadratic approximation to our original function. So as long as our point of reference or our points of interest are near 1, 1, then this will on average give you decent approximations, a lot better than our tangent plane approximation. Up to this point, we've been looking at tangent planes and Taylor series for functions in a very pure and analytical manner. Let's actually look at a very applied example of how Taylor series can be used in real life. Let's assume that the sales of a business are a function of its price. Let's assume that this price is going to be denoted as P, and marketing budget. And let's assume that this is going to be denoted by M. But we don't know the exact mathematical relation between these variables, which is often the case, especially if there is a sense of randomness in the purchasing power of the customers, and also the marketing budget, and also the price. So let's assume that the company sells 1,000 units at a price of $50 with a marketing budget of $10,000, right? And let's assume that the sales of the business are denoted by S. So just from this starting point, what we have is that S is a function of the price per unit and the marketing budget per unit, right? And that's per unit. Actually, sales would be in units, right? So from this first piece, so we're going to have 1,000 sales is going to be equal to S evaluated at 50 per price and 10,000 for marketing budget, right? So there's our price, there's our M value, and there's our S value, right? So this is pretty much our point of interest for a Taylor series approximation. So that would be our 0th order approximation, right? Which is not very exact, right? But there's a bit more information so we can at least get a first order approximation. If they increase prices by $1, they sell 10 fewer units, right? So how can we map that out in terms of derivatives? So if I change the price, so if I take the derivative of S with respect to price at this particular point, 50, 10,000, that's going to be approximately equal to, because it's a estimation, we're going to have a decrease in 10 units, right? And keep in mind that's in units per dollar, right? And similarly speaking, if they increase the marketing budget by $1,000, they sell 50 more units, right? Now keep in mind this needs to be in units per dollar. So what we need to do is we need to divide this by 1,000 and divide that by 1,000. So we have $1 and then they sell 50 divided by 1,000 units. So from that information, if we take the derivative of S with respect to M at this point, 50 and 10,000, that's going to be approximately equal to 50 divided by 1,000. That would be equal to 0.05 units per Right? So we have that information. And keep in mind, 50, 10,000 is our point of reference. Right? So that means, even though we do not know the function S, which is a function of price and marketing budget, we know that this is, at least in analytical form, approximately equal to S at AB, and then plus S with respect to P at AB times P minus A, and then plus SM at AB, and then M minus B. Right? So that is our first order approximation, and we would have to be given a little bit more information in order to get our second order approximation, which we don't have. So using this particular structure, we have that SPM will be approximately equal to AB is 50, 10,000. So that's going to be approximately equal to 1,000. And then we have our derivative term for P at our reference point. So that's going to be equal to 10. And then we're going to have P minus 50. And then we have our next derivative term, 0.05 times M minus 10,000. So this is going to be our approximation, and we can distribute and simplify that if needed, but in some sense, that's technically all you need. So as long as you estimate around a price of 50 units and a marketing budget of 10,000, this will give you on average the number of units that you will sell. Now, from this, you can actually get approximations for the derivative of S. So if we take the differential of this particular object, what you're actually going to have is the derivative with respect of S is going to be equal to, so 1,000 will be a constant. This is going to be equal to minus 10 dp, and then plus 0.05 dm, right? Because 10 times 50 is a constant, 0.05 times 10,000 also a constant, right? So we get this relationship as well, right? So if we increase our price by, let's say, $2, and also increase our marketing budget, let's say by, I don't know, let's say $2,000, how much will our units increase or decrease? This equation can help us answer that question. So using this relation, we're going to have that ds will be approximately equal to, at least from our first order approximation, of minus 10. So our sales is going to be increasing by 2. So our price is going to increase by 2. So dp will be equal to 2. And then our marketing budget, dm, will increase by 2,000. So just simplifying that out, that's going to be approximately equal to 80 units. So if we increase our price by $2, which is going to be, a little bit more sadder for the customer, and if we increase our marketing budget by $2,000, so that's a little bit sad for us because we're spending more money, even though we're getting more sales, we're only going to be selling on average or approximately 80 units from this approximation. So our question on the business side is this change in the number of sales worth it? Because we're spending $2,000, we're losing money potentially, and we're also losing customers since we're increasing price. So is an increase in 80 units really worth it? That's for the business to decide. But that's one of the many applications that you can actually use multivariable Taylor series for. Hope you enjoyed this video, and I'll see you in the next one. Take care.